Problem number 23. So if the sum of three numbers is 0, prove the following two identities. The first one is very famous identity, in fact. So it's like if you are preparing for some kind of math contest, it's good to memorize that. So that's like a cube plus b cube c cube minus 3abc. So this expression can be factorized as a plus b plus c, and then the second factor is squares minus ab bc ca. Yeah, I think that's the correct one. So when you set this one equal to 0, you will get that the entire this side is equal to 0, and that makes a cube b cube c cube is equal to 3abc. So just like taking cubes is basically equal to multiplying those three numbers, right? So that's the identity. That's a very important identity that you should memorize, and then whenever you need, you can use that. But in this video, let's try to avoid this identity and try to prove it. So the first one. So let's try to simplify a cube, b cube, c cube, and try to see if we can get something like 3abc. So what's the approach? So we can start by, for example, we can start let's say a, use the sum of cubes formula. Here we have b plus c cube, and then the formula for b square minus bc plus c square, right? And then again, I can rewrite this in the following way. A cube plus b plus c. This is, I can rewrite it as b plus c square minus 3bc. So if you open the parentheses, you get like 2bc minus 3bc. So that gives you what you need. So now I can replace b plus c. So what's b plus c? B plus c is negative a. So b plus c is minus a. I can replace with b plus c with minus a. That gives me a cube plus, we have minus a, and minus a square, and minus 3bc. Now just open the parentheses. So, okay, let me open these parentheses, a cube minus a. So that's just like a square minus 3bc. Now if I open the parentheses, I get a cube minus a cube plus 3abc. So this is 0. That makes 3abc. So basically, a cube, b cube, c cube is equal to 3abc. That's the first part. Okay, now let's try to prove the second one. So what can we do with this 3? Maybe, again, try to use something like this. B plus c, where do you see b plus c? You can see b plus c here, right? You can take out b squared, and then you're left with b plus c. Also, you can take out probably a squared, you're left with a plus c. So let's do all of this. So a squared left with a plus c minus abc, and then the last one is b squared is c plus b. So let me replace this one with minus b. So we have a squared multiplied by minus b, that's abc. B squared multiplied by minus a, negative a. Or rewriting a squared b minus abc plus minus b squared a. Now I can do something. Okay, looks like I can take out ABC here. ABC is common factor. Minus ABC, no, AB. AB is a common factor. Inside the parentheses, I'm left with A from the first one, C from the second one, and then B from the last one. So since this is 0, I have minus AB times 0. That's 0. So this expression is 0 if A plus B plus C is 0. So that concludes the proof of both identities when A plus B is 0.